Let me give you the link to the stream and also test the audio. Mhm. Audio is good. Here is the link. Oh, wait, we're in this room. Okay. So it's going to be in the side chat. Here's the link.
Okay.
And let me send an invite to anyone else who wants to join. There you go. Okay. So your proposition is that GR might have singularities?
Yeah, it definitely has singularities. There's no question there.
Okay, so let's define singularity. Singularity is.
It just you write down a theory with equations, and at some point in those equations, you get something that equals infinity. That's a singularity.
But I mean, that's infinity. That's not a singularity. Singularity is something else. It's not else, I'm sorry. Singularity is similar,
Mhm.
but not necessarily that. Singularity, from what I understand, it's just a region or solution or point that we simply don't understand in any system
Yeah, yeah.
in a mathematics.
That's true.
Okay. I mean, I wouldn't say it's true. It's just the definition. It's just it's that's what I heard from a guy that does a lot of math.
Yep. It's a definition. Okay, I'll tell you where the two converge. If you write down a physical theory, every physical quantity is finite. There's no thing in physics that equals infinity, like actually.
Mm-hmm.
So if you write down a theory and you get something that equals infinity, it means that you don't really understand it well enough, and that's like it's kind of a breakdown of the theory.
I don't know. I wouldn't phrase it that way. I would say
Hmm.
you don't know. You just don't know. If you get some weird result, an unexpected result that like an infinity or something else.
Hmm.
I don't know. I maybe I don't know. But yeah, infinity is certainly confusing. So you just don't know if right because as you said, an infinity in real life, um, it's weird. It's unexpected. Anyway, it's not so clear.
Sure.
The problem with the proposition that let's write it down that G. So you claim GR has definitely or might have.
It definitely the the theory definitely has singularities. Okay, like if you think a point in space that has infinite curvature is a singularity, then yes, it has a singularity. If you don't think that implies it's a singularity, then I don't.
We can just say infinities because singularity we actually don't know what we mean. So I can do singularity slash infinity, right?
Sure.
Because you claim you can create an infinity in GR, right?
Yeah, yeah. You in the theory, there are solutions to the equations that govern GR in which you get a point in space with infinite curvature, which to me is non-physical.
Okay, but the math of GR, would you say that is GR, or would you say
Hmm.
that is the math of GR?
It's GR. GR is the math that's GR. GR is a model. The model is math.
I would say no. I would say you can talk about GR with no math, right? You
You can talk about it, but you're not doing GR with no
no no
math.
no, but fine. I mean the historically what happened is that Einstein thought of he realized the equivalence principle,
Hmm.
and then he realized how gravity works,
Hmm.
and then he went to study math. He went to study. I forgot the name of his teacher, who was an expert at curve geometry, and he went to
Hmm.
study the math of curve geometry, and
Yep.
so he knew GR before he knew the math of curve geometry, as far as I know.
He had a bunch of ideas that he couldn't formalize, right?
But
But once, like when he wrote down the general theory of relativity, that was a mathematical theory. Like in his paper, like his actual publication about general relativity, that's where he wrote the Einstein field equations down.
okay, let's all right. But we know historically it was fine. The paper fine, but we know historically what happened. We know that he didn't
Hmm.
know curve geometry mathematics, but he did come
Yeah,
up.
and he
Mhm.
right. He had a bunch of ideas, sure, but I would like it's not the theory of relativity until you formalize it in a language that can actually describe it, which it is the theory in its math.
Look, I can explain the notions of general relativity and
Hmm.
then and without math just build a computer simulation that makes the same
No.
why not?
Well, how do you build the simulation,
Just based
right?
on right. General relativity sits on top of an intuition, nothing else, right? It starts from the equivalence principle, nothing else.
Right, but like okay, let's say you're trying to in a computer program simulate like two bodies orbiting each other, right? So you have their initial positions and you need to find out what their positions will be at the next time step. How do
Mhm.
you do that without the Einstein field equations?
I would write. It's a good question. I haven't done it, but I mean, the universe does it without Einstein's field equations. Einstein's field.
Right,
Hold,
right.
wait, just one day.
Oh, sorry.
So
Mhm.
Einstein's field equation is just a model of
Right.
reality. Reality
Hmm.
doesn't use Einstein's field equation to know what to do. So Einstein is just a theoretical model. In reality,
Hmm.
it does whatever it does. So I would say that we can simulate reality directly in a software simulation, and we can completely skip over the math.
Hmm.
Why?
So,
Yeah.
um, you're right. Reality just does whatever it does. Nature just does whatever it does. But that's the whole point of it being a model. Like doing, like writing a simulation in general relativity isn't doing anything in nature. It's writing down a model of systems. You can't simulate anything unless you know, like, like the way that computer simulations work for general relativity is you know where things are now, and you need to predict where they will be in a second. And in order to make that prediction, you have to write down the equations.
I don't
You
have to.
can't.
I don't need to.
So then do it. Make a prediction about where
I'm
Jupiter is going to be
I'm
tomorrow.
not. That's different. I mean, I can tell you how to do it. I mean, I can explain it to you right now. I can explain to you how exactly gravity works. How
Sure. So
exactly.
give
Mhm.
me your explanation of given Jupiter's position right now, how you can predict where it's going to be tomorrow in like a program.
That that wouldn't be GR. That would be the primitive case of GR, the degenerate case of GR. That would just be Newtonian. I mean,
No, it would be you have two very massive bodies going very quickly, so you are well within the relativistic limit.
I would say,
We
I would
that's why
say,
there were corrections to the orbit of Mercury.
okay, okay. So I would tell you, like, look, I mean, they've been able to, at Newton's time, and I think maybe even Galileo, they used to be able to predict the motion of the planets very accurately.
Right, and they were wrong.
Well, wait, according I mean, as far as I know, when we go use rockets, we use Newtonian equation. We don't use Einstein. Like
For rockets, sure. But like for example, Newton tried predicting the orbit of Mercury, and it turns out that he was wrong by a relatively small amount, but he was still wrong enough to detect with just a regular telescope. And that was an unsolved mystery for a while until the equations of general relativity came out.
yeah,
Then people actually solved for the true orbit of Mercury and found that it actually precesses. And they wrote down the solution and it actually corrected. And with GR, we can now fully capture and predict the orbit of Mercury with the Einstein field equations.
Okay, can you look? So look, when you're asking, so I would ask. So if I were you, I would ask me to explain Mercury from first principles without by skipping the math. But I would tell you something else. I mean, I can easily build a computer simulation that uh, predicts the flow of time. Right, without math, I can slow down time. That's easy, right? You
How? Do it.
I mean that it comes directly out of Einstein's thought experiment with the ticking photon clock. Right, you always imagine a photon clock. You put it
Hmm.
on the surface of a mass, and then you increase the
Hmm.
mass, space flows through the ticking photon, and because
Hmm.
the speed of light is constant to an inertial observer where geometry, the curvature is zero, so it seems
Hmm.
like the clock is ticking slower. This would be a piece of cake to create a simulation that does it. That's zero challenge.
So,
I don't need math.
given a clock that has 10 kilograms of mass, how much time dilation is there? Can you give me a number?
No, I mean, I don't think so. Einstein, as far as I know, he doesn't predict the constants of nature. Like he feeds in constants of nature. As far as I know, at least C he feeds in. I don't
That's
think
not that. Oh, yeah, sure. So you feed in C, but you can still make predictions. Given a planet of X mass, this is how much time dilates. Can you do that for me right now in a Python program? You said it's a piece of cake.
no. I mean, I, what I'm saying is, I can explain it too if I need to. I can explain it, and then to convert an explanation into a program, it's straightforward. I can
Okay, so to explain how to do that.
I just did. So you have a
No, you didn't.
mass. Okay,
Yeah.
I'll explain again. I don't have a problem. Look, so according to Einstein, mass curves the geometry, which causes
Mm-hmm.
which causes space to flow into the mass.
Mm-hmm.
So now imagine the clock at the surface of this mass, and imagine this
Mm-hmm.
space like a liquid that flows, like a river that flows through the clock. The faster
Mm-hmm.
the river flows through the clock, the more of a distance the photon needs to travel between the mirrors.
Mm-hmm.
That's it.
Sure. So, okay, that's a good story with a lot of concepts, but you said the words mass curves geometry. How much mass gives you how much
I don't,
curvature?
the,
Can you tell me that? Yeah.
no, I don't think Einstein predicted capital G. I think capital G shows up as a given in
It's
his.
not that's not about predicting capital G. That's not the point. The point is you input capital G,
Yeah,
and
of
that
course.
tells you how much mass gives you how
Yes.
much curvature.
Yeah. Yeah. I mean,
So, can you tell me how much mass gives you how much curvature? What's the equation for
I
that?
don't need to. When you write a computer program, so the constants you put like in a text file or like a
Mm-hmm.
configuration file, or you make a UI and you're able with a sliding thingy, you play with it until it looks like reality. But to write the
That's
program, mhm.
so. If I ask you, how fast does a clock tick on Mercury, given that it's X number of pounds? How specifically, step A through Z? No, like, you know,
I told you, I gave you all the steps. You can ask me.
you
Go ahead, go ahead.
okay. Um, Given that it weighs 10 tons, how fast does a clock tick? Give me a number.
So we would need to calibrate the program. So we would write the program, run the simulation, see what it looks like, get the results. We would actually see, for example, how fast uh, a test particle falls at the surface of the Earth, and we would calibrate the program to make it 9.8 meters per second. Once that's
Mm-hmm.
calibrated, then the result for Mercury should come out without any more tweaking. We just need to calibrate it
Calibrate what? What are we
with
calibrating?
simulation. We play with this with.
And
Go ahead.
so, what is the simulation doing?
Basically, it's a UI. It's a user
Mm-hmm.
interface that
Yeah.
you can you can input whatever system you want, single planet, mini planet, whatever you want
Mm-hmm.
you input, and uh, anything, and then you give everything mass, and you program the
Mm-hmm.
simulation so that okay, that's the first step. The next step is you can the space that all your masses are embedded in, you in the software you actually treat it as a liquid, like water,
Mm-hmm.
that is 100% viscous. So anything that
Mm-hmm.
sits in it is completely dragged into the object. But if
Mm-hmm.
it's
So
traveling, yeah, yeah, go ahead.
how does a computer simulate the motion of water?
Probably like I think in a good simulation, the best simulations would be finite element analysis. Like
Right. What do you input to those?
like it depends on what package I'm using, but if it's like an advanced, let's
Mm-hmm.
assume we have an advanced package that we can just throw in objects, define their masses, and then embed them in
Mm-hmm.
a liquid that we can define.
So
Go ahead.
from the beginning, let's say you want to create a finite element simulator.
No, no.
What do you
Usually you buy those. Those are packages. I mean, I can.
Well, sure, but how do they work? That's what I'm saying.
So it's a.
You're starting from the solution of, oh, you just throw objects in and watch them move. But how does the actual simulator work?
You're asking me the people that write finite element analysis packages. How did they build their
Yeah,
package?
that's kind of the that's the ultimate question here, right?
No,
Finite element simulation works because you input the Navier-Stokes equation.
no, 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 no.
Yes,
No,
that's how they work. You can
no, 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 no. There's you take look. You take a finite element analysis package that you can do whatever you want with
yeah,
it. Look,
uh-huh.
I haven't played with anything that's available in the market. That's not my line of work. So, but in the old days, I did things like that. Anyway, if there isn't such a package, I'll create such a package. But
And how does it work? Here's a finite element simulator. You can see it inputs equations. It inputs the Navier-Stokes equation, right? And in order to do GR, you can't just use the Navier-Stokes equation.
right, right,
That's
right.
like,
I went through this with someone else. Yeah, yeah. Navier-Stokes are not proper. So I need the liquid in which uh that imitates space, that simulates space, is different. It has different properties.
right. That's called the Einstein field equations. So that's what you would
Exactly.
need to
I
solve.
don't need them. I don't need them. No, no, no. I don't need them. All I need to do,
So how you said that
basically,
you need finite element analysis
yes,
to do your simulation. And in
yes.
order to do that, you need an equation that tells you how each finite element
I'm not.
moves.
I'm not even sure.
Navier-Stokes doesn't work for that, so you
I
need
didn't
to use
ask
the
them.
Einstein field equations.
No, no, no. I'm not going to use anyone's equations. Look, let's even scroll back from uh, finite element analysis. Now that I'm rethinking it, we can actually run a simulation with actual particles that because
Yeah,
finite element analysis, like you would divide your space into a grid, a 3D grid.
right.
And we could do that, but then you have to define like these cubicles, and I'd rather not.
Hmm.
We can actually create a liquid out of particles that has a certain property.
Right. That's yeah, sure. You can just write it down as a continuous thing. That's fine too.
Right. Look,
What governs their motion?
right. So I didn't go through all the steps yet, but
What guides
however,
their motion is Newtonian physics or just physics in general,
ri-
right? You have to write
no,
equations.
no. I want to skip Newtonian. Right. We want to skip Newtonian. Newtonian is a degenerate case of GR. So I don't want to
Hmm.
feed in Newtonian. Newtonian comes out of the simulation.
Sure. I'm asking you, how do you feed in Newtonian or how do you feed in GR? How does that work?
So we look. The trick is to properly define and simulate the liquid that we call space and the geometry that it flows in.
Okay. And how do you do that without the Einstein field equations? You
So
can give like you've given like a weird example where you're like take a clock, put it on a planet, and light is blah blah blah. But like I'm asking, like actually, how do you, given a planet that's X mass, how do you?
it doesn't matter what the mass is. So
It does.
listen. I told you we'll calibrate at the end to get 10 meters per second squared for the surface of Earth. That's at the end. But
So how do you do it for Mercury or the sun, or
okay,
if it's spinning, or if
once
it's charged?
fine. So well, look, we can come back to the charge and the spinning. If we skip spinning for now, of course that's going to simplify it. Look, I'm answering all your questions. We can. I didn't go through this exercise all the way. It would be a very nice exercise to actually do it. But the fact is, of course, we can do it. Just like Einstein did it, modeled his ideas in mathematics, I can model it in a computer simulation. There's no reason why I
They're
should.
the same though.
No, no,
The math and the computer simulation
it
are the same. The computer simulation
no,
just solves the math equations.
no.
Yeah, that's how a computer simulator works. If you want to argue with me, make the computer simulation yourself and see at which point you need to enter the math.
I actually agree that it is. It might end up. I might end up recreating the differential equations. The
No, you
Einstein.
end up solving them with a computer. You don't recreate them. You have them. Einstein gave them to you. Then you plug them into a computer simulation. But
Let,
ultimately, it
hold on,
comes
hold
down to the equations.
on, hold on. Let's see. Look, let's assume nothing is spinning. Let's assume we're just taking a mass and a test mass, and we're dropping it at the surface of the Earth, and we're
Hmm.
observing, right? Like I would do it right now, and I would observe, of course, that it accelerates at about 9.8 meters per second squared.
Hmm.
Now, I want to build a computer simulation that does the same, right? You'd agree that that's not difficult, right?
Yeah, that's not.
So, but you would say, yeah, but you'd use Newton's acceleration. So I would say no.
Yeah.
So I would not. I would actually use a liquid. And I would say that Earth sucks in this liquid. The surface,
Hmm.
let's discuss it as if the Earth is flat. So the
Hmm.
Earth is going to suck in this liquid at at a certain rate. I don't know at what rate. At a certain constant rate.
Hmm.
And the question is, does it have 100% viscosity? No, it doesn't. It's going to. I didn't think about that. Mm.
Hmm.
Okay, but all of this is very nice. I mean, we can imagine. Look, we can. Right? Einstein developed GR from his intuition, right?
Hmm. Notice he said developed with his
Yes,
intuition. Not
right.
that the theory is intuition.
But it's based on intuition, right?
I mean, intuition and thousands of experiments, but yeah.
No. Wait, what experiment? I didn't know that there's any data that went into. There's no references in his paper.
Oh, I just mean the verification of the theory.
No, 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 no. The theory was presented with no references. Maybe reference to his previous paper. I don't think there's any.
No,
No, there is references.
I don't know if there's specifics, but
I
like
don't.
the reason that the theory needed to be invented was basically because there were open questions within physics that like experiments were showing that that there were discrepancies between Newtonian mechanics and what we actually observe, such as the precession of the orbit of Mercury.
Okay, but Einstein, when he developed GR, he didn't use any data. He except for
It's not about data. It's about like, for example, particles entering our atmosphere that technically have a half-life of a nanosecond, but somehow survive their journey all the way to the surface of the Earth. Newtonian mechanics doesn't describe why that is able to happen. There were a bunch of paradoxes at the time. Electromagnetism was a big one, right? You have an electric field; it goes a certain speed. It's observed at a certain velocity, but relativistically, or according to Galilean relativity, if you go to a different reference frame, you observe a different electric field. How the hell does that work? An electric field is an observable quantity. It shouldn't depend on the reference frame. There were really a lot of paradoxes. The precession of the orbit of Mercury. If you plug in Newtonian mechanics and you try to predict how Mercury orbits, you get the wrong answer. So all of these things came together. That's what Einstein was thinking about.
wait.
And
When he created or derived GR,
mhm,
what data did he use besides the equivalence principle? Basically, an assumption. What do you need?
um,
If I asked you to derive right now from first principles GR, what are the principles that you need?
there essentially is no principles. Like there's axioms. There's no first principles derivation of the Einstein field equations. What you can do is you know that mass generates curvature, and you know that stress energy generates curvature.
How do you, wait?
And you can
That's a
just
given.
assume that
Wait, that's a given. That's
no, it's not a given. It's
what's
an
a
assumption.
wait. Right, but isn't that the what do you call it? The equivalence principle assumption?
No, no, that's just like you if the thing that you're postulating is that um, gravity actually works because of the curvature of space-time, then one thing that like in order to match observations, you have to say, well, that curvature needs to be proportional to the mass, or more specifically, the stress energy.
One second,
And then
wait. I want you to
mhm.
derive GR from first principles. So go ahead.
So there is no first principles derivation of GR.
Okay,
I'll
derive GR.
give me a second.
Okay. Sorry.
Sure. So um, anyway, the way that this works is you need a model that matches observations. What are the observations? Well, the observations are that stress and energy, the stress energy tensor generates curvature in space-time.
Wait,
That's the observ
that's the observation that Einstein started from?
yes. That was the whole curvature thing. Yeah, that was like the epiphany is that hold on, there's the equivalence principle. Why is there an equivalence principle? It's because it's actual curvature. Curvature affects everything, not just,
Oh, okay.
you
Yeah.
know.
So fine. Yeah.
So hold on.
Go ahead.
I'm still going.
I'm sorry.
So
I'm sorry. Go
um so then you have an equation like this and you're like, okay, how the fuck did he come up with that? That's insane, right? So okay, you you know that stress and energy generate curvature just because that's an observation and you want a way to describe it. Um, so the right, that T mu nu, the capital T thing, is just all of the mass and energy within a region of space. And the thing on the left is just the amount of curvature in a region of space. And all he said was these two things are proportional. And what's the proportionality constant? That 8 pi g over c to the fourth? Well, it just needs to be whatever matches observations. Turns out that's 8 pi g over c to the fourth. It really is no more complicated than that. So the assumption there is that the curvature is linearly proportional to the stress and energy, right? In general, he could have written something like G is equal to constant times T squared, right? There's no reason it has to be a T. It could be a T squared, it could be a T cubed, but he was like, let's go for the simplest possible thing. Let's just say it's proportional to curvature is proportional to the stress and energy. Um, and then from here, you take these equations and you solve them and you see how um, you see what predictions you can make by just making the simple assumption. And it turns out that it predicts every known phenomena that we've seen. That's it. It's you assume that it's as simple as possible. Turns out that the simplest possible answer is what describes everything.
Wow. Wow. That's like the best explanation I've finally heard of GR derivation. Phenomenal. Good job. All right. So so of course as you explained it, you said that Einstein came up with an idea in his mind. Let's go for the stress bends, or the stress causes curvature,
Mm-hmm.
meaning energy and mass cause the geometry to curve.
Mm-hmm.
So that's an intuition, right? You can easily intuit it, right? You can think about any tiny cubicle of space and say, okay, in
Mm-hmm.
that tiny space there is some energy and mass, and therefore there's
Mm-hmm.
going to be curvature, something like that.
Yeah.
That tiny space is going to be curved like this, like that, because of energy and mass. All right.
Correct. Yeah.
So so a singularity, let's say, is an infinity. How can you get an
Mm-hmm.
infinity in such a case? Right?
Sure.
From
So
this,
let
yeah.
me get there.
Hmm.
Yeah. Yeah. So um, it comes down to how the hell do you define curvature? Curvature is the thing that we're trying to talk about. Just saying the word G with the subscripts mu and nu doesn't tell you anything, right? Um, so G is proportional to this thing called the metric tensor. Let me find a thing for that. Um, hold on.
When we were texting, I thought you were going to be mean, but you end up being nice.
No. Um, so da, 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 da. Sorry, I'm looking for the correct tensor. It's actually surprisingly hard to find. Okay, so found it. Great. Okay, so this G is actually all of this stuff. Um, so this is the left-hand side. It's this really complicated mess of bullshit. And then the right-hand side, let's say it's just a planet, right? So that's you want the stress energy tensor for a planet.
Hmm.
And
Wait,
it comes down to salt. Yep.
wait. G is the curvature, and the curvature
Yeah, G is the curvature.
on the right side is still the expansion of G, or is it something else? It's just the expansion of G.
The Yeah, yeah. The right hand side of what I just wrote is like the explicit expansion of what G is.
Okay.
So what we're really solving for is lowercase g. I'm looking for. So we're solving for this thing. It's going to be kind of blurry, but this thing is what we're actually
Got
solving
it.
for.
Okay.
That's what tells you the geometry of space.
Hmm.
So when you plug in on the right hand side that T mu nu, the expression for a planet, which I can look up in a textbook or something if you want, or you can just like I can just link you the textbook later. You can look at the derivation.
Hmm.
What you end up doing is solving a really complicated equation for for this little lowercase g as a function of capital T.
Hmm.
And what you end up with for a massive body is, give me 1 second.
Hmm.
Um, the solution that you end up with is this. This is the final solution to uh, what we call the metric.
Hmm.
Okay. So R underscore S, this thing,
Hmm.
called the Schwarzschild radius. I'm sure you've heard of it.
Oh,
That's
yeah.
yeah. Okay. So um, below the Schwarzschild radius, that's where things start to get a little bit weird.
Hmm.
Um, you can see that if r is equal to the Schwarzschild radius, what does that second component become?
When when they're equal, when RS equals R, it's one.
Yeah,
So it's zero. I mean,
it's one divided by zero,
okay.
right?
Hmm.
That's bad.
Okay. So I mean, all that means is because we're comparing to c, it just means the speed of light. No,
No, there's no comparison to see here. That's just like
I mean the
this is
curvature. When you say the curvature, is this the event horizon?
so yeah, the r is equal to rs is the event horizon. Something completely different happens at r equals zero.
So this is where, at this point, I would say, okay, I don't understand all this math. Let's go back to the intuition of GR, and let's think
Mm-hmm.
about the black hole and the event horizon, and see what's going
Mm-hmm.
on there, and see why the equations, why the results are bizarre. Maybe
Mm-hmm.
we misunderstood something because it's many steps and a lot of very complicated math, but it all starts from intuition. So we can always go back to our intuition and think about the case of a black hole. And
Right.
I've thought about
I'll
black.
I'll I'll put it.
Hmm.
Sorry,
No, go ahead, go ahead.
that was it. This solution that I've given you has um, what's it called? It's been exactly accurate in every experimental effort to predict orbital motion or really anything that we want to do in physics.
I understand. I understand. I'm not saying
So
there's
if
anything wrong with it. I'm saying I don't know what's going on here. I didn't follow the math. I didn't derive it.
oh yeah, that's the problem. Nobody does.
Well, you don't know.
Like if people understand the math. The problem is, you can't. Um, Nobody understands why it blows up the way that it does.
But
That's the problem.
that's
That's the singularity.
fine, but that's the singularity in the mathematics. If we go back to the intuition, I don't have a singularity in my intuition. I know exactly what's going on at the event horizon. I can derive the event horizon from first principles in 1 minute or even less. I can
So do
derive,
it.
yeah, I can derive the event horizon directly from Newtonian mechanics, from Newtonian gravity.
Do it.
Newtonian.
Yeah.
So uh let's think about it. Yeah, I actually did it. I have it on a paper, a piece of paper right in front of me.
Hmm.
So if you start, can I take a snapshot? Let me see. It's on two pieces of paper, like scrap papers I had here. Uh, is this enough? Uh, Let me see. Do you want to see the snapshot?
Sure.
Okay. I mean, there's other people who derived Schwarzschild radius from Newtonian gravity. I'm not the first one, but I'll gladly share it
And you
with you.
you
I'm very proud.
sure you get the correct answer.
Of course, everybody does. It's easy.
Okay. Let's see
Directly
it.
from Newton. Just that Newton didn't know the speed of light. He thought it's instantaneous. But if you told Newton the speed of light is a constant, then he would tell you fine. Then just plug in C for V, and you get RS. RS is easy.
Hmm.
RS is a joke. Let me just take it. I don't want to, because I'm such, I'm afraid of my privacy. I don't want to be doxxed. I just need to make sure
That's fine.
I'm not taking any picture of anything personal. My desk, of
Hmm.
course, is a mess because it's a mess. Why would it not be? Oh, let me try that again with Flash. I mean, I was going to go through it in a separate video, but if you're curious to see my work, I'll gladly share it. Oops. I mean, I can derive GR. I can show that you can see the curvature directly from Newtonian field equations. I mean,
Okay, so show
curvature,
me.
the curve geometry comes directly out of Newtonian gravitational vector field equation. I'll show you in a second. Let me just make sure again and again that there's no personal information on this thing. Okay. Uh, this is so dangerous. Oh my god. Am I doing the right thing? Let's take a wild chance. Okay. Um, Let me look on my phone first that I didn't share any. Oh, everybody can see it already, so it doesn't matter. Okay, so there it is. I hope there's no, there's no private information. Yeah, it's pretty good. Okay, so we start with acceleration at r equals gm over r squared. So that comes out of, if you, I'm sorry, I skipped the first step. You just multiply both sides by the test mass, by m. So on the left, you have MA at R, which is just MA equals GMM over R squared, right? You can see it on my video.
Mm,
If you
yeah,
if you go to my
that's
YouTube.
fine.
Yeah, okay.
Mm, yeah, that's
So
fine.
my question is, what is R, right? R at T equals what? I don't know why. I mean, because you need an intermediate variable because the definition of A is a function of time. So
Mm-hmm.
R of T is equal to the square root. Right. So you bring r to the top. You cross, right? So r squared is on the top left, and a goes down, and you square root both sides. So r is
Mm-hmm.
a function of t, is the square root of gm over the acceleration as a function of time. The next step, I just drew it.
Mm-hmm.
So acceleration versus space. So the acceleration at any point, according to Newton, of a test mass. So you already see that light would be affected by gravity because the test mass,
Why?
because the mass drops out. It doesn't matter what the mass is. So Newton, if Newton would not have gone to manage the mint, if he would have stayed in physics, he would have figured it out. He was right there.
Hold on. No, because let's see, capital G M little m over r squared. Yeah, if you start from m equals 0, you just end up with with 0 equals 0.
No, no. M drops out. The test mass drops out from both sides. It could be zero, right? You can, as little m goes to zero, the equation
Hold
holds.
on. No. Okay. You've done like algebra, right?
I've done much more than algebra, as you can see here.
Okay. So if you have an equation like,
Yeah,
ax squared equals b, right?
but m
What?
is not
Hold
m is
on, hold on, hold on.
it's not the
I know.
denominator. It's the numerator. There's no problem
I
to
know.
go ahead.
One no, no, no. 1 second. So
Hmm.
you start with an equation like ax squared equals b, right? You want to solve for x. So what do? You divide both sides by by a, right? If you do that, you get x squared is equal to b over a,
Okay.
right?
Uh,
So
whatever.
there's something you have to do when you do this. That is, you have to check that a is not equal to 0.
Yeah, but we don't.
Otherwise, it doesn't work.
But we don't have that because we have MA
We
equals.
do.
No, we don't. We have
We
M.
have
No,
ma.
no, we don't. No, no, no. Look, it's
We have
MA.
ma is equal to gmm over r squared,
Yes.
right?
So the
That's
M.
the initial equation.
Yes, the little M's
But
drop out. They can be
they
zero.
don't just drop out. You have to divide by m. In order to do that, you have to check that it's not equal to 0 because you can't divide by 0.
Okay, but you agree that M can be any mass, right? It could approach zero. There's no problem that M should approach zero.
It could approach 0, but it can't be 0
But it
because you
could
can't divide by
fine.
0.
It could infinitesimally approach zero, right? There's no problem. You can approach zero forever and ever until it is right?
there's a big difference between
No, there isn't.
infinitesimally close to
No, there
zero
isn't.
and actually equal to
No,
zero.
there isn't. No, there
That's the
isn't.
whole point.
No, 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 no. If you can infinitesimally approach zero, that's good enough for reality. For then light is good enough.
What is does light have zero mass or infinitesimal mass?
We don't know actually.
It has zero mass.
How do you know?
What do you mean?
How do you know?
Because if it had mass, it would be exponentially suppressed. Like the electric field would have been exponentially suppressed.
Oh,
That's the whole point of screening
okay, fine.
is
Look,
that
look, look, look. All I'm saying is light could be as light as you want. I'm sorry for the double entendre. Light can have any mass you want, as little as you want, and
but not zero.
fine. But
Okay, but let's move on from this
yes,
anyway.
yes, 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 yes. Okay. So we see the
Um,
curve. So we see that A. Now A is that is the curve geometry. So you already see that we're talking about a curve geometry because right
there's
acceleration.
no curvature in A.
No
It's
A
just acceleration.
right, but that is right. That is I to me it is to me that is curvature. That is
How?
curvature because a test mass would accelerate. That is
Yeah,
curvature. So
but it's same thing with Coulomb's law. Coulomb's law is not curvature.
anyway, okay. I mean, fine. I mean, we can come back to this. That's fine. Anyway, so basically that, and then I'm looking for v, but whatever. So a equals gm over r squared.
Mm-hmm.
That's from before, and now I'm defining a as dv dt, and dv dt now is equal to gm over r squared. And dv
Mm-hmm.
dt you can multiply by, I think it's, who knows, is it dx dx? So dv dx times dx dt. So there is like another variable that I'm shoving in there, isn't there? dv dt, so it's dvdr, sorry. dvdr
Mm-hmm.
times dr dt, right? You're allowed to do that
Sure.
because
Yeah.
dr is just one. And
Yep.
okay, so dvdr times v, because dr dt is v. Is dr dt
Mm-hmm.
v? Well, yeah, because r
Yep.
r is the
Yeah.
location of the
It
particle.
is.
Okay, so dvdr times v is equal to gm over r squared. So vdv, now we're multiplying both sides by dr. So vdv is equal to gm over r squared times dr. Okay, integrate
Oh, where did you get DV?
dv. You can trace it. What do you mean? You can trace it from a. A is dv dt.
Yeah, yeah. I know A is dV/dt.
Okay.
Okay, then you have V dV/dr is GM over R squared.
Wait.
I see that.
Just before the integration, right? We're at the
Yeah.
I didn't number
Yeah, yeah.
stuff. So VdV is equal to GM over R squared times dr. No?
Whoa. There's no V dV.
Yeah.
There's dV/dr times V is
dV,
GM over R squared.
but you multiply both sides by dr.
Okay, that's not how that works, but
What do
I'll
you
I'll let
mean?
that go for now.
Wait, what?
Oh, differentials aren't fractions. You can't just multiply them. But anyway, I'll like
Okay, I don't see
um
the problem. I mean, I've done
that's
this a million times before in class and stuff. I never noticed an issue.
then your teacher was anyway.
My
Let's pretend.
my teachers in all my books, everyone. Okay, I mean, look,
I promise you, your books do not tell you you can multiply differentials and just cancel them. That's not how that works. If you can show me a textbook that says that, I'll grant you. But that's not.
I'm not gonna tell you how many years ago it was. My God, I'm so old. All right. So we
So
got
VDV.
VdV is equal to GM over R squared times dr. Integrate both sides. So V, we're integrating
Okay.
from V equals 0 at infinity to V equals some V1 at the radius that we're looking for. This is going to be the Schwarzschild radius at the end when we'll plug it in. That's equal
Um,
to the integral over R from R equals infinity to R equals the Schwarzschild radius R. So of gm over R squared dv,
Wait, hold
dr.
on. I need to think about this integral for a minute.
Sure.
Okay, so you're integrating this over a path. So you're integrating from time equals 0 to time is equal to some t.
No, there's no time here. I'm integrating v dv from v equals 0, the velocity is 0 at infinity, to the velocity is equal to some v1 at the Schwarzschild radius. It's going to end up being c. That's going to be c.
No, so how? Okay, you're integrating both sides. In
Yes,
order to do that, you have to integrate both sides with the same bounds.
these are the same bounds. They're corresponding. There's complete
Okay,
correspondence.
so
V.
you're telling me that at
Let,
v equals 0, r is equal to infinity?
let me explain. I didn't explain to you what's going on. So I'm placing, because I'm assuming curvature. So I'm placing a test particle at infinity, and at
Okay.
infinity there's some gravity already. So
Hmm.
at infinity the v is going to be 0. The velocity of the test
Why?
particle. I'm running a test. I want to.
Okay, sure.
I'm assuming space time is going to flow into this black hole, so that space time is
Hmm.
flowing at c at rs. So at the
Okay.
radius, at the Schwarzschild radius, space time will flow in at the speed of light. So I'm
Hmm.
taking a test particle that's going to be dragged in by space time from infinity. So I'm assuming the curvature at infinity is almost 0, right? Because I'm assuming A
Hmm.
is curvature. So I'm assuming I'm being Newton, but I'm assuming a theory of gravity that space time is being, sorry, no time. So space is being dragged because of the curved geometry. Space is being dragged. It starts at 0 at infinity, and it reaches the speed of light at the
Hmm.
Schwarzschild radius, at some radius. At that radius,
That's
the speed of space is going to be the speed of light. What?
what? That's no, that you
I'm
don't reach
assuming.
the speed of light.
Yes,
You don't reach the speed of light at the Schwarzschild radius.
that's what I'm assuming. What do you
That's
mean?
not true though.
What do you mean?
You can reach the
That's the event
you can
horizon. That is exactly the event
no, you don't
horizon.
no, you don't reach the event horizon at C. No, if whatever it is has mass, it can never reach C. That's not the point. You
It's a
can reach
test.
the event
It
horizon
doesn't matter.
at 2 miles an hour.
All no 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 all no no no. It's being dragged by space at the speed of space. The viscosity is 100. In space has 100 viscosity towards the
What?
mass. The space is a liquid that
Uh,
drags you
s-
100%
Space space does not have
in the direction.
viscosity.
So in my model, that's why I told you I have a model that has nothing to do with GR. So in my GR, I'm using
Hmm.
space that has 100% viscosity in the direction of gravity. So
So
when
if you have viscosity, what does viscosity also tell you?
no, there's no mass.
No, it's not about mass. What does
Okay.
viscosity tell you?
No, there's no loss of energy. It's 100%. 100% viscosity, zero loss of energy.
No.
That's
A
just
very high viscosity means all of the energy is lost. That's what
okay.
viscosity
I'm
means.
why? But there's no friction in the system. Okay,
Viscosity is
wrong,
friction.
Okay, so not viscosity. So whatever is embedded in this liquid is It doesn't matter. Whatever. I'm just assuming that space has a property like a river, like in all the simulation, all the computer simulations that all the YouTube creators make. So imagine you put a
Hmm.
ship in the water. The ship is not moving relative to the water, but the water is flowing in. At infinity, now
Hmm.
imagine that the gravity sucks in the water. All the water is being sucked in.
Hmm.
At infinity, the flux is 0, but
Hmm.
at the gravity well, the flux is maximum. Let's define the flux, the speed of the water flowing, to be the speed of light at some radius. That's going to be our Schwarzschild radius. The point mass at infinity starts at 0. The water is barely moving there. It's at infinity, it's not moving, but
Okay,
there is
so what you've
curvature.
solved for is at which radius from the massive body does your object approach the speed of light?
No,
That's
reaches.
not
It's not the object.
reaches the speed of light.
It's not the object.
Guess what?
It's
Right, right. So guess what Newtonian physics doesn't take into account?
what?
That you can't get to the speed of light. That's the whole thing.
Uh,
The whole Newtonian mechanics says you can't reach the speed of light. That's why you need Lorentz transformations. That's why you need modified Newtonian mechanics. That's,
uh,
eventually that's why you need GR.
wait one
The
second.
source field radius has nothing to do with
Okay,
the
let me
fuck.
think 1 second. So I'm observing an object, of course. So who's observing this?
What do you mean?
So if I'm observing a black hole, right? I see
Mm-hmm.
space flowing in faster and faster as space gets closer and closer to the so-called event horizon. At the event
Mm-hmm.
horizon, space reaches the speed of light.
No, it doesn't. Nothing reaches the speed of light.
No, space doesn't have a problem reaching the speed of light and going above the speed of light. Nothing is going to
Space
tell.
doesn't move. At anything traveling towards the event horizon doesn't move at the speed of light, except for light itself. Like if you throw a car at the event horizon, it's not going to reach the speed of light. It'll like actually probably slow down as it approaches the event horizon.
No, that's not. That's counterintuitive. I don't accept this interpretation. Nothing can. Why would it slow down?
It might be counterintuitive, but it's very much what happens. Because you have time dilation. That's basically why. As you approach the event horizon, time dilates. You starts to, and outside observer will time getting slower and slower, the body moving towards the event horizon until it seems to stop.
No, the clocks of someone resisting the flow of space will slow down, but someone flowing with the flow with space, well, relative to me, the space is flowing, so I'm looking at it as if it's moving really fast. Let's assume
Here,
that
one
I'm
second.
what your connection is bad.
No, no, no. I'm just pulling up Wikipedia.
The question is, wait, let me think about it. What are you gonna see? Look, you could say that the clock, if there was a clock particle, then that clock would tick slower. Maybe, I'm not even sure. Yeah, because
Mm-hmm.
if we're observing from flat space, then we would see the clock ticking. What happens to space? I think space maybe would stretch at that point.
It would contract, and time dilates.
No, the clock slows down relative to an observer at flat space. So far away at flat space, at flat geometry, sorry, the flat geometry far away, there's someone sitting and observing. And
Mm-hmm.
he's looking at the clock of the traveler, as the traveler is the test particle, and the traveler has a clock, and that
Mm-hmm.
clock. So you could say that as far as the observer is concerned, the traveler is moving faster and faster, and the traveler doesn't know why. Sorry, the observer doesn't know why the traveler is moving faster and faster. All the traveler, let's say, he doesn't see the black hole, so he must assume, okay, this guy's just going faster
Mm-hmm.
and faster. Therefore, his clock must be ticking slower and slower. So,
Yeah, sure. Look, I'm just gonna go back to your equations that you wrote down. You wrote v squared over 2 is gm over r, right? That's the bottom of the page,
look, you could say that I'm getting the same
right?
paradox as Schwarzschild, but I don't need Einstein to develop the Schwarzschild
No, no, no.
radius.
I'm I'm pointing at that equation. V squared over 2 is gm over r, right?
Right.
That's
So
an equation you wrote down?
Right. So the
Okay,
integral
so what?
is v squared over 2 from 0 to v1 is equal to negative gm over
Uh huh.
r from infinity to r.
Right,
So you plug in the
and then the one
values.
right below that.
So v1 squared over 2 minus 0 is equal to plus gm, because it's minus, it's infinity to minus. At
Yeah,
infinity,
yeah.
it's 0. So then it's
No
negative.
issue with that.
Okay, so it becomes positive gm over r. And at the top
Yep.
on the
No
right,
issue.
we.
No issue with the bottom one.
Okay,
No, no,
so
no, not the top of the right. Let's focus on the bottom left, the one you have boxed.
sure.
V squared over 2
Hmm.
equals gm over r.
Sure.
What happens when r equals 0?
It's so that's an artifact of the assumption that we have a point mass at r equals 0. You'll get infinity. So it doesn't mean anything. You can ignore it.
Sure, but point masses exist just fine.
No,
Electrons are point masses.
no. What's your evidence that an electron is a point mass?
Yeah.
What's your evidence?
Okay, I'll give you an even easier one. Let's say you have a small then we can go over that later. That's not the point. Let's say you have a small object. What happens if you plug in a small number?
Your connection is horrible. You're bouncing in and out. What are you offering? I'm sorry.
Let's say r is very small, arbitrarily small.
Okay. R of what?
What happens to v?
R of
Big
what?
R, the one you have at the bottom.
Okay, it's arbitrarily small.
The,
Then, I mean, we're solving for r. We're assuming we're looking for light speed. What happens to r?
but it goes both ways. You can solve for v or you can solve for r.
That's
They're,
fine.
right,
Yeah, you
doesn't
get.
matter. You
Yeah,
can look at what you can ask what the velocity is as
it's fine. It's fine. You.
right. What happens when you
Yeah, you can get higher than the speed of light motion. That's fine. There's no issue with that.
it, there's a lot of issues with that.
No, there isn't. What's the issue?
Nothing can travel faster than the speed of light.
That's not true. What's your evidence for
What can
that?
travel faster than the speed of light?
No, nothing can be observed to be traveling. You cannot observe it. Of course, it can travel faster than light. I mean, right now, on the other side of the
No.
universe, yes, right now, on the other side of the universe, there is galaxies traveling faster than the speed of light relative to us. There's no issue with that.
Where there is a lot of issues with
Certainly,
that. That's not true.
certainly beyond the cosmic horizon, they're moving faster than the speed of light. That's why they're beyond the cosmic horizon.
No,
Look, if I
that's
have
not why.
here, I'll
It's
prove it to you.
because light. It's
No, no,
actually
no, no. Here,
no,
so
no, no. One
I'll,
one second, Lib.
I'll easily prove it to you that it's possible to travel. Of course, look, there's a guy to my right.
Okay, sure, yeah.
There's a guy to my right
Mm-hmm.
traveling at 99% the speed of light to my right, and there's a guy on my left traveling at
Mm-hmm.
99% of the speed of light to my left. As far as I'm concerned,
Mm-hmm.
they are traveling away from each other at almost twice the speed of light. That is the truth,
No,
undeniably. Wait,
that's
what?
not that.
Wait,
No,
wait.
that's not how.
Then what?
That's not
Okay,
how velocity
hold
addition
on. Then
works.
what is,
And
according to me, by my perception, what is their relative velocities to each other? According to me,
sure,
by
give me
my
one
observation.
second. Yep, one second.
Sure.
Here it is. Here's the velocity addition formula for a Lorentz transformation.
No, just
Special
explain to me.
relativity.
I'm observing someone traveling to my right at
Yep.
almost the speed of light, and a guy to my left
Yep.
traveling to my left at almost the speed of light. As far as I'm concerned,
Mm-hmm.
they're traveling away from each other at twice the speed of light.
Mm-hmm.
What? Yes or no? What am I missing?
No,
So explain. I
that's
then
not
yeah.
that's not how Lorentz
I don't
transformations
care.
work.
I
No,
don't care about
you
Lorentz.
don't.
I'm observing.
You can't.
No, no,
You
no.
can't add velocities like that. That
What do you
only
mean
works
add?
for low speeds.
What do you mean add? As far as I'm concerned, this guy's moving to my right. He's going to reach Alpha
Yeah.
Centauri in X time, and the guy to my left is going to reach
Mm-hmm.
whatever target at that time. They're going to cover, as far as I'm concerned, they traveled away from each other at twice the speed of light. What are you talking about?
No, they're
Yes.
not traveling away from each other at
As
twice the speed of
as
light.
far as I'm concerned, they are. Definitely.
What?
Yes.
It's not. It's not how
Each
velocity addition
no, no, no,
works.
no. Each one of these guys,
Uh
they are
huh.
observing the other. They cannot observe each other traveling faster than light.
Yeah,
But I,
that's like the day zero question of special relativity. That's why special relativity needed to get invented, is because that's not how it works. And so people were like, "What the fuck?"
one
And
second.
they invented special
Let me
relativity to
understand.
treat that
Wait a
exact
minute.
case.
Hold on.
This is
Hold on,
yeah,
hold on. So you agree that at, let's say, 51% the speed of light, there's barely any time dilation, right? It's barely noticeable. Even I think at 80% the speed of light, still relativity is barely noticeable, right?
that's not true. No, after 30%, relativity is noticeable.
Okay, fine. Let's say there is let's say the guy to my right is traveling 1 light year to my right at
Mm-hmm.
51% the speed of light. The guy to my left is traveling to my left 1 light year away to my left. As far as I'm concerned, let's say they both traveled at almost the speed of light. The guy to my right will reach his
Mm-hmm.
target after 1 year. The guy to my left will reach his target after one
Mm-hmm.
year. Right? I don't have a problem.
Sure.
So as
In
far as
your
I'm
in
concerned,
your reference frames, the
so
targets are
yes.
just closer.
So as far as I'm concerned, no. At my reference frame, they are the target is exactly 1 light year to my right, 1 light year to my left. That's measured. There's
Mm-hmm.
no dispute. I don't care what they experienced. So the guy to my right
Mm-hmm.
took a year, according to me, to reach the target on my right. The guy on my left took a year to reach his target, as far as I'm concerned. And now they are, after a year went away from my life, they both reached their targets. They are now separated by 2 light years away after 1 year. So as far as I'm concerned, they must have traveled at twice the speed of light. As far as I'm concerned,
Mm-mm. No, because
away from each other.
that's not
They must have traveled away
okay.
from each other at twice the speed of light. That's absolutely what I just witnessed.
No,
Yes,
no.
yes,
You witnessed each one of them individually go below the speed of light.
yeah.
That's
Ninety nine
from
point
your
nine,
reference frame. Is you
almost
sure?
ninety nine
So
point nine. Yeah.
you watched you watched each of them individually going lower than the speed of light, and then in each of their reference frames, they'll see the other one going lower
I
than the speed
don't
of light.
care. I don't care. As far as I'm concerned,
You- At,
they traveled away from each other at twice the speed of light.
but nothing's moving faster. There's no object moving it faster than the speed of light. So I
That's
don't know
not
what you're
true.
talking about.
That is not true. It's the
What
limit of
object is moving?
No. It's the limit of observation. You cannot observe anything moving faster than the speed of light. In
So what
reality,
object in that example moved faster than the speed of light? Point to one.
in reference, they moved away from each other. As far as I am concerned, I measured them moving away from each other at twice the speed of light almost.
The distance from two objects is not an object itself. What object moved faster than the speed of light? I'll
Look,
put it this way:
relative
if
to
you
me,
wanted to make a
relative to
Mhm.
me, they each move just under the speed of light. I agree with that.
Sure, great. So
But
then nothing moved faster than
but
the speed of light.
I have to conclude they moved relative to each other faster than light. I have to say that. Otherwise, I'm held in contempt of court.
Sure, and that's fine, but nothing actually moved faster than light.
Of course,
The
relative
distance
to
between two objects,
fine, but
the distance between two.
fine. Look, what's the point? Look, the point is, as far as I know, for example, space, the universe is expanding faster and faster and faster and faster, and there is a cosmic horizon, but there's
Mhm.
galaxies that are beyond the cosmic horizon. That, as far as we're concerned, what does it mean to be beyond? It means they're traveling faster than light relative to us. That's why they're out.
No,
Yes,
no.
yes.
Why is it a cosmic horizon? Why?
Because anything past it can never interact with me. It's done.
And why can it never interact with you?
Space is expanding. Look, space we know
Why
is
can it never interact with you?
because they're limited by the speed of light relative to me.
Correct. Yeah, they're limited by the speed of light. It cannot Nothing can travel faster than the speed of light,
No,
so it can't reach you.
that's
That's
not true.
why.
That's not true.
That's why there's a cosmic
That's
horizon.
not true.
That's
You
it.
cannot make that statement.
You
That's
just said it yourself.
no. I cannot observe. I cannot observe anything traveling faster than light. You don't know what reality is. We don't care what reality is unknown.
Okay,
Stop saying that things cannot travel
I have
faster.
to go, but
Thank you very much. I appreciate your time. I mean, I really enjoyed it. I wish we can continue some other
yeah,
time.
yeah.
All right. I'll let you go. Wait, are you gone? Oh, he's gone. Who is Amber Gerand Fries? Do you want to talk? I gotta go very soon. Let me see. How long have we been here? Okay, I'm alone. Okay, now in 10 minutes. Anyway, it was a good debate. Very interesting. I got things off my chest and I showed you guys a little bit of my mathematics. Let me see. Wait, what happened to. Uh, where did I put it? I guess here? Okay, here? Where did I put? Oh, here. Yeah, so this is my derivation of the Schwarzschild radius based purely on Newtonian field equations, vector field. Oh yes, there's no vector. Did I put a vector? No, I didn't put a vector. Yeah, it's radially symmetric, so there's no need for a vector. So this is the Newtonian curvature, which Newton, I think, could have achieved. He could have come up. The problem is he didn't know at that time that there is a speed limit to light. But I don't know if that's critical. I mean, he would not have thought to calculate the Schwarzschild radius. But later on, people realized that there is a limited, speed of light is limited, and they calculated the Schwarzschild radius without GR. You don't need GR for the Schwarzschild radius. I don't know why everybody is so delighted. You don't need GR, you don't need general relativity to create a black hole. You just need the speed of light. Once you know the speed of light is some constant number, it's not infinite. I think that's it. That's all you need. Now, he did ask a good question about the speed of light. What would we observe? So I thought that it's really simple, but now I see there is an issue because if I see the test particle falling towards the black hole, as it's coming closer and closer to the event horizon, it's supposed to go faster and faster. It's supposed to reach almost the speed of light and then cross the event horizon and continue going faster than the speed of light. How can it do it? How can that be done? It has to come in super fast and collide with the event horizon at light speed, but I cannot see it traveling at light speed. Wait a minute. I can see it traveling at light speed. That's not true. But I cannot see it traveling faster than light speed. So it's gonna this guy is gonna appear like it's traveling. Oh, it could even be a planet. There's no problem. It's going to just have a lot of energy, so get out of its way. But it's going to be traveling at the speed of light as it goes through the event horizon. There's no issue. Why would I have an issue seeing something, right? I don't have a problem observing particles close to the speed of light, right? We bring particles, hadrons, in the Hadron Collider to 99.99999 the speed of light. There's no issue with that. So we're just going to see it traveling at almost the speed of light. Doesn't matter what its mass is. And once it goes through the event horizon, it's gonna look to us like it's moving only at the speed of light because we cannot observe it going faster. But I think it's just going to look like it's continuing to fall into the black hole. My intuition is it's just going to look like once it passes through the event horizon, we're still going to see it. It's going to look like it's falling into the black hole. Now, in reality, it's already inside the event horizon. But to us, all we're going to see, right, we cannot see, right, the whole point of the internal of the event horizon is that no light can come out of it. So once they cross the boundary of the event horizon, they have to poof, disappear at once. They just vanish. But there can't be a point, right? There's no there has in nature there's no discontinuities. So it must be a well-behaved function. So it must so light reaches so as it reaches the speed of light, something must begin to happen so that there is a continuity. So maybe it starts blacking out. It must something happens as it smacks against the event horizon wall. To us, this is just what it's going to look like to us. In reality, it's going to zoom right through the event horizon. To us, nothing beyond the event horizon can transmit any information. And we don't want it. Oh, this is what they meant. Now I'm beginning to understand. But this has nothing to do with the singularity at the event horizon. There's no singularity. We just have to think what happens at the event horizon. Now, inside the event horizon, we know what happens. Space just continue moving faster and faster. And then later, it's going to, at one point, when it reaches the bottom, the neutron, right? At the bottom of a black hole, there is a neutron, a compressed neutron. And as light reaches that neutron, inside that neutron, right, at the center of the neutron, the flux is zero because of symmetry. So as it enters the neutron at the center of the black hole, it's going to start slowing down. What is going to slow down? So everything keeps hitting that neutron. Everything that falls in accelerates. So that neutron, well, I need to think about what happens to that neutron. Let me see what time it is. Okay, we need to get moving. Anyway, this was extremely interesting. Oh, I love these discussions. Finally, I'm talking to normal people. This guy is really good, really good. Really, I really appreciate everything he had to say. A good explanation of GR, of the mathematics of GR. Good stuff. Good guy. Definitely appreciated. Anyway, that's it. Thank you everyone for your attention. See you later. Bye bye.